today. This is a video showcase for a package we developed called Automata, consisting of building blocks for experimenting and uh, playing around with automatons, specifically DFAs and NFAs, as well as with regular languages and regular expressions. So first, let's visit each module one by one, each files in the modules. Here, on the topmost here, we have the DFA file, which contains the DFA class that inherits from the automaton, which we will visit later. This class requires five set of parameters called the states, the alphabets, the transitions, the initial, and the accepting, all of which are representations of the elements in the five tuple, which formally defines a deterministic finite automata. The states being Q, the alphabet, the sigma, transitions, well, it's not directly a one-to-one translation, but is a code implementation of the transition function, the initial or starting, and the accepting or the final. So here's the initialization method. First, we validate the aforementioned parameters. Then we set the attributes of the object. And here are the methods. The most important is the traverse, which processes an input string by looping into the input symbol by symbol, then checking in the delta function what the destination state is given the current node and the current symbol. And if there is no transition, that means it's a dead state. So we return false. Otherwise, we check if it is in self-accepting, then append it into the current node, which is the list that we uh, keep to list down the set of the states that are already visited. It will keep continuing it until the string is exhausted, and then returns whether whether the input is accepted or not. The method that we actually use to check if the string is accepted or rejected is the accepts method, which just calls the traverse method but returns the valid part or the boolean part. The straight transition, on the other hand, also calls the traverse method but returns the list of states. The delta function, well, it's obviously the equivalent of the delta function in real world or theoretical automata theory, which takes in a state and a symbol and returns the the destination state given those two parameters. And if there's none, then the current symbol is a dead state and returns none. Otherwise, if the state is not defined in the transition that is mentioned beforehand here, then it will throw a key error because it is not found in the dictionary. The, the validate transition is simply a checker method when initializing a DFA object, and it doesn't really matter on the actual process that the DFA does. The last method, the print transition function, is simply a helper method for printing the transition attribute into a nice formatted output. So here are the examples of the DFA class. The samples file contains a number of samples or sample DFA objects that implements a specific kind of regular language. So here, the variables are meaningful, which describes what the object does. For example, this one is a DFA for even number of zeros. The second is an even occurrence of each character, and the other ones no max substring and no MA plus, which means A plus then X substring, and their equivalent regular expression shown above. So these sample objects are actually the ones we have defined in the paper that list down the four regular languages that we will be implementing as per the requirements of the project. So next is the DFA, the NFA. I mean, the NFA is a bit more complex than DFA. Namely, it involves new features such as the epsilon closure, the epsilon transition, um, which requires us to implement additional logic to introduce new methods that will help us traverse and do the things that an NFA does. So, for example, here is the epsilon closure, which method which returns a set of states that, given an input state, we uh, we reach those states given one or zero or more epsilon transitions. So there's a code, and also we have methods for concatenating, combining, for clean star, and clean plus of different NFA objects, which we will see later on. The syntax, I mean. Um, Above here, we have two internal methods, the merge initial and the merge accepting, which are just because NFAs can have multiple initial and multiple accepting. So these methods provide a way for us to merge them by calling only one method. The merging process only involves adding a new state and then adding a epsilon transition to each of those previous initial or acceptance states. And is also um, an important method, the 2DFA method, which converts the NFA object into an equivalent NFA that recognizes the same language as this NFA. So the process is quite lengthy and involves a few loops that requires the union of subsets and epsilon closures and such. And right at the end, we return the DFA object with a new set of states, the same alphabet as the NFA, obviously, the transitions of the new DFA that we have calculated above, the new initials, and the new accepting. The traverse, it's similar to the DFA equivalent, but it also involves getting the epsilon closure of the current of the node of the current state that we're in, and involves an any, which is a simple line that returns true if any of the visited lines is an accepting, and so we return true if that's the case. Accepts is the same as the DFA, the transitions is the same. The delta is also similar, but not the same. It returns an empty set if it's a dead state, and not none if the state key if the transition does not have a transition from the state and the symbol. Again, the validator transition is simply a checker function, and the print function a helper function for printing the output of the delta function or the transition function. The epsilon, I've mentioned earlier, the NFA involves epsilon transition and epsilon closures. Well, we've provided a class and a singleton object for representing those kinds of operations, special and specific to NFAs. So the epsilon state is simply a name type or a, a class for typing, which provides us as a neat way to represent null moves or e-transitions in the code. So this is the epsilon that is used in the NFA for indicating that a transition is involves an epsilon or does not accept a symbol. And application example of it is here, where for example we have this NFA and define these set of states. So in this line, it means that from S0 with an epsilon as a transition, meaning it doesn't consume any symbol or character, then these two states are its possible destinations. That's about it for NFAs. Let's move on to regular expressions. Now, regular expressions are a, uh, a pattern of symbols and operations that represent a type of regular language which which matches the patterns of that particular regular expression string. So, for example, we have here a regular expression like this, like an A star B union C. A regular expression um, can have three operations in it: a union, which is the vertical bar, a star, which is the clean star, which indicates that a character before it, for example, this A, can be present in the string zero or more times. And there's also a variation of the clean star called clean plus, which just means that the character preceding it could appear one or more times. So that's about it about on regular expressions, on the syntax of regular expressions. How do we actually parse it or um, do something about a string like this? So you've probably seen these are the processes on converting a regular expression into a NFA. So the methods involved in that process includes the tokenize method, which accepts a regular expression, which is a string like shown before, and looping individually each character in that expression and determining what type it is. Is it either a character, a operation of union, an operation of star, clean star, an operation of clean plus? Is it a parenthesis? And if not, then this method will throw a parsing error, in meaning that the token or the symbol in the regular expression is found to be not recognized. After after tokenizing the regular expression, which returns a list of um, on this structure, a tuple of a string and the symbol, the type and the symbol. So, for example, a union, then this one would be the bar. If it's a star, then it will return star and the asterisk, and so on. In the parse method, uh, this one implements the shunting yard algorithm, but is modified to support clean star and clean plus, which are unary operators, or an operator that only requires one operand, and it is less left associative, meaning it only modifies or operates on the left side. Um, well, it's very complicated to explain it, and if I do, then this will be a long video, so I will not bother to go in depth. But the base general gist of it is there are two data structures being used: the output queue and the operator stack. The output queue contains the um, the ordered series of characters and operators, so that when it is processed eventually, the computer will uh, will have an easier time processing the parsed tokens. The operator stack is a auxiliary data structure which temporarily holds the operators and pops them and appends it back to the output queue depending on the precedence and the order or the type. For example, the the expression inside a parenthesis has higher precedence than any other one. So it will parse that first and then continue parsing the other in the correct order of precedence. So after that, it will return the output queue, and then finally, the compile method takes that output queue or the parse tokens and looping through it, iterating each parse tokens one by one, and then applying operations such as if it is a character, then create an atomic NFA or an NFA with only one symbol. So, for example, if that token is A, then the atomized NFA is a starting Q0 with an transition of with A to a accepting state Q1. So it only involves two states and one transition. But later on, if the regular expression is more than one character and involves operators, then it will apply the appropriate operation, such as a clean star, as what we've seen earlier in the NFA class, and a clean star plus, which is a flag which indicates that the clean star refers to the plus variant. Again, the plus operator is a accepts or is represents that the symbol is allowed to be present one or more times. And lastly, the union, which just combines both NFA1 and NFA2 with no complicated process. If if there's an index error, meaning the number of tokens is insufficient, then it will throw out a parsing error again. And but if there's no error, it will concatenate all of it because it's simply the result of if there are any uh, if there are any NFAs left in the stack, it will just concatenate all of it and then return the correct NFA output. Here's the atomic NFA. I have mentioned it earlier, which just creates a new state with one transition of symbol. So that's about it in the regular expression. The automaton class is an abstract class which serves as a parent for both DFAs and NFAs. Given that it is a class method, it doesn't actually implement any logic inside its methods, but rather delegates the exact logic on its child class. And we've decided to do this because the NFA and the DFA have somewhat varying level of difference in their methods. Others are the same, such as what we've seen in the accepts and the state transitions method. Others, like the traverse, is a mildly different implementation, and so we left the exact logic of their processes in their corresponding child classes. So here again, the validation methods are also defined here. Um, the new unique state is just a helper state to return a new state with a unique name given an NFA or a DFA object. It's useful when uh, we want to perform union, concatenation, or clean star because those involve creating new nodes and add new states. I mean, and adding transitions between them. Lastly, the state, the most bare building block in this package. The state is simply a wrapper class for what we would call a state in an automaton, which is just as a node in a directed graph. If we turn a DFA into a visual representation or graphical representation, so it's just a simple class that accepts an optional parameter called name. You can either explicitly name a state or leave it for the class to automatically set a name for itself. So for in this line, for if a new instance of a state is created, it will set the name as a base name, so Q, and an instance name. Uh, for instance, if we run the program for the first time, it is set to 0. Then it will set its own name as that, Q0, for example, and then increments the instance counter. So the next state will become Q1, and the next Q2, and the next Q3, and so on. And the other ones are these dunder methods are just These two in particular are used to allow the states to be stored in a set, because a set in Python, or well, in general, does not accept non-unique states. So we have to make sure that each state we create, each instance of a state class, is unique on its own right, so that it can be stored in a set. And the other two are simply to uh, make the printing or the output of a state object nice and good looking, or rather easy to look. Others are just helper methods such as set base name. So you don't really want to set the name to other types, um, variable types or data types, but rather you use this to ensure that the name that you want that you entered have the right data type, which is string. And the reset naming just resets the class attributes or static methods to the default Q and 0. And the last one from set is just a useful helper method involving the subset construction, as we've shown earlier in the two DFA class of the NFA to create a equivalent DFA class. So the tests here are a set of test suites or modules for testing the correctness of code and implementation of the different modules and classes and methods that is defined in this package. So if you run the test, it finishes with no errors and all passed. You can, this is too long to show in one video, so if you want, you can look at it through the link given in the documentation, the paper. So as a demo, to demonstrate the effectiveness and uses of the package, we have a demo file that we can run. Demo the file and see here. So we imported the sample we've seen earlier, the even number of zeros from the DFA module, and check if the string 00100 is accepted in this particular DFA. And if we see the output below, number one, it is true. And the expected answer is true, and it's correct. The second one, 10, it doesn't have even number of zeros, so it is false. And now from a DFA sample, NFA sample, we have A or B whole star, meaning parenthesis A, B, parenthesis A, union B, parenthesis star. So meaning it accepts 0, A, or B, and repeat 0 or more times. So an empty string is 0 because it is clean star, so true. It's A because it is a union, so it's also true. And A, B, 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 A is also true because of the parenthesis. Next, the RE to NFA. RE given is A star B union C. If you want to be correct about it or reduce the confusion, you can say that A B then B C, B or C. So that's the output or the pedantic way of structuring this NFA. So first, we tokenize. Given that this does not have any invalid error and is formatted in a correct syntax, then we expect no errors to be thrown. So here it tokenizes it correctly, the character A, the character star, the character B, the union symbol, and the character C. We parse the tokens into postfix notation, meaning the operators are now on the after the operands. So, for example, a plus b in postfix notation would be ab plus. So here, because clean star is already in postfix, so no changes there. But b or c, for b or c, the resulting postfix, as expected, will be b, c, or. And now, finally, to compile and turn that regular expression into an NFA, we have this transition function, which, according to my testing, is correct. Just trust me on that. Okay. And now, but if we want to don't deal with any of the manual processing of the regular expression, we can just directly put it or pass it to that 2NFA method, and it will have the same the same transition function as the manual parsing and tokenizing. NFA to the FA. You just have to trust me on this, but given an NFA with states Q0, Q1, Q2, Q3, and alphabets 0 and 1, and these transition function with an initial state of Q0 and an accepting state of Q3, the equivalent NFA function, DFA, using the 2DFA method will become this. Now, this is correct, but you just have to trust me on this, but this is correct. And the accepting, it shows here the last line is the equivalent DFA is accepting, which because the sample NFA has the state Q3 as the accepting state, then any subset state in the DFA containing Q3 will also be an accepting state. So here it correctly outputs that it is the same. Or maybe I can show you the correct syntax here. For, give me a moment. Never mind. It doesn't want to show itself. Right. So that's basically it for this demonstration and showcase of the Automata package. If you wanna see the whole code base and um, watch yourself how the code works or understand more of what we've made here, you can visit the web page or the repository for this code base at github.com/pyquint/automata. Thank you very much and have a nice day.